In this screencast, I'll be going over the handouts that you have on Canvas. They're all in one document, and they summarize several of the key ideas throughout the entire chapter. First thing I'd like to talk about is just about the nature of sound itself right here. Sound is a compressional wave. Sometimes we call that a longitudinal wave, like when you squeeze a slinky together and that compression in the slinky travels down the stretched out part of the slinky. This has been or will be demonstrated in class. It is not a transverse wave, something that vibrates up and down, and related to that, it's not an electromagnetic wave, which we'll be talking about later when we get to electricity and magnetism and the electromagnetic spectrum. A sound requires a medium, some material through which it can travel. In other words, sound is not going to be able to travel through space because the medium is extremely minimal. You have about 1 particle per cubic centimeter, and that's not enough to sustain a compressional wave, which requires a collision between the particles that make up the medium. The word medium here, again, is the stuff through which the wave is going to travel. Another point is that we have the speed of sound can be calculated in a number of different ways. One way to calculate the speed of sound is to use this definition, that the speed of sound is 331.5 meters per second, and for every degree above 0 Celsius, you add on 0.6 meters per second, and for every degree below 0 Celsius, you subtract 0.6 meters per second. You'll be doing this type of calculation an awful lot in the homework and on the test whenever you're working with the speed of sound. This translates to roughly 1,100 feet per second, which would be about the length of a soccer field or football field from the back of both end zones. Now, when we talk about what makes one sound different from another, we have 3 components. For example, 2 sounds can be different because they have a different loudness. When we talk about loudness in everyday language, we might use the word volume. But in physics, we would talk about the amplitude of the wave. Sound is not a wave that involves it's not a transverse wave, but if we were to represent sound as a transverse wave, you could have a small amplitude and you could have a big amplitude. And the amplitude is the distance from the equilibrium point to the crest or to the trough. You can have a small amplitude or a big amplitude. The unit of loudness is the decibel, and you see the term deci there, 1/10 of a bell. And Bell, named for Alexander Graham Bell, the guy who invented the telephone. The range of decibels typically is about 0, which is the threshold of hearing. Below 0 decibels, you cannot hear the sound, depending on the frequency a little bit. And then when you get up to about 100 to 120 decibels, this is going to be very, very painful and might even damage the tympanic membrane in your ear, your eardrum. Now, we use decibels because a bell is too large of a change in sound, so we talk about a decibel instead. You'll be learning in this chapter how to calculate decibels. Now, the second quality that makes, or component, I should say, that makes one sound different from another is imagine you have 2 sounds that are the same loudness. Maybe a So those 2 sounds could be the same loudness, but they would have a different pitch. And in everyday language, we might say, well, you got a high sound that's way up here. Or a low sound, that's way down here. And in physics, we call that different frequencies. And you can have a high frequency or a large frequency or a small or low frequency. And we measure frequency in cycles per second, how many vibrations per second there are in this sound wave, or we could say how many compressions and rarefactions there are in a sound wave. Another unit would be s to the minus 1, which would be 1 over s, where s would be seconds. And a cycle per second is a hertz, named after Heinrich Hertz. And typically the human ear can hear from about 20 to 20,000 hertz. So 20 hertz would be a very, very low sound, and some animals can hear a sound at a frequency lower than this. And then 20,000 hertz is the upper limit of human hearing, or 20 kilohertz. And as you get older and your eardrums are less and less sensitive, oftentimes because of damage from hearing very, very loud sounds over the years. In my case, growing up mowing lawns, both for my family as well as on the job, that those loud noises, I never wore earphones. And nowadays I do as I mow the lawn, but I think the damage is already done. I can only hear up to maybe 15 to 16,000 hertz. It's very high frequencies I can't pick up. And that's not atypical. Now, you can have two sounds that are exactly the same volume and two sounds that have exactly the same pitch, but you can tell the difference in the quality of sound if one of those sounds was made by a violin and one by a flute and one by a trumpet, for example. And that is because these sounds have what we call a different harmonic content. And harmonic content would be a combination of frequencies that make up the quality of that particular sound. And the way in which these harmonics, and there might be 4 or 5 or 6 significant harmonics, and even more harmonics that are not quite so significant, that constructively and destructively interfere with each other. And that's what gives the unique quality of sound to a violin or to a trumpet or to a flute. And of course, the quality of that sound is going to depend somewhat on the construction of the violin or the trumpet or the flute, and what it's made out of and how carefully it's made, and so forth. So these three things are what make one sound different from another. Now, also in this chapter, when we make a graph of the volume of a sound with the frequency of a sound, you can see that depending upon the volume of the sound, we are going to have different sensitivities with the human ear to the different frequencies and volumes. And the phon, P-H-O-N, or maybe phone, but it's the fen, some pronunciation kind of like that, is a way of representing the perceived loudness of sound. And perceived, of course, means that we go from the threshold of hearing, which would be an average of many, many human beings, all the way up to the threshold of pain. And of course, the threshold of hearing is different for different people, and the threshold of pain is different for different people. So in any case, this is very similar to the decibel. And right here. Now, you can see that when we talk about very, very low frequencies, which will be down in this range, that we can't pick up sounds very well until they get up to about 60 decibels. The typical human language is, if we're just having a normal conversation, it's in this region of the 70s of decibels. Sometimes when I'm teaching, I'm up in the 80 of decibels because I'm trying to emphasize the sound, speak distinctly, and also project to everybody in the classroom. Now, you'll notice that I can't hear or humans in general can't hear soft sounds that are in the low pitch or low frequency. It has to be about 60 decibels. But when we get up to about 1,000 to 5,000 to 10,000, we can hear those sounds much more easily when they are soft. And you'll notice that this scale down here is a logarithmic scale. And the decibel, by definition, is a logarithmic scale. So you have two logarithmic scales on each axis. Now, as far as the threshold of pain is concerned, you'll notice that I'm much more sensitive. In other words, pain is going to be achieved at a lower volume, let's say 90 decibels, 95 decibels, at frequencies of 1,000 to 10,000. But I don't experience quite as much pain until I get to 100 or 110 decibels at these low thresholds of hearing. Now, the last thing I want to comment as far as this graph is concerned is that babies, very young children, can hear these higher frequencies but much better than they hear these lower frequencies. And typically you'll notice that as you interact with a baby, you have a tendency to speak with a higher pitch. And you might, as you encounter a baby, you don't talk to the baby and say, "Hi, baby, how are you doing? Are you having a good day?" Not that the baby would necessarily understand your language, but they also would not necessarily respond to you because they don't hear the low voice. And you instinctively begin to raise your voice and you say, "Hello, how are you doing? Are you a nice little baby? Don't wet the diaper when I'm taking care of you." And when you speak with a higher pitch, because the baby is more likely to respond to you and interact with you, at least visually, at a higher frequency. Now, we're going to also learn in this chapter that you can go from your perceived volume of sound in the decibel to an actual metric unit of watts per meter squared in terms of the intensity of sound. Now, the next handout has to do with the Doppler effect. And if you were standing beside a road and an ambulance was going by, you would hear the ambulance coming down the road towards you, and certainly the volume of the pitch of that siren would get louder and louder. But interestingly enough, the frequency or pitch of that sound also gets louder and louder. And then when that ambulance is right next to you and passes on by, not only does the volume get less and less as the ambulance recedes from you and eventually you can't hear it at all, but the pitch also has a tendency to drop. So the pitch has a tendency to come up and get higher and higher and higher, and then it drops and goes lower and lower as that ambulance goes by. And so it would sound something like this. You would hear the pitch get higher and higher and higher, and then as it goes past you, the pitch gets lower and lower and lower. Again, I'm talking about the pitch, not the volume. Now, when we measure the Doppler effect, which is that apparent change in frequency of the pitch, even though the ambulance or the fire engine or the police car is making exactly the same pitch sound, which is what the driver of the vehicle would perceive, the perceived pitch or frequency primed, it needs to be adjusted. What the actual frequency is and what you hear are going to be two different things. And you can calculate that in the following way. Let's suppose that you are traveling either towards or away from the speed of sound. From the you, the observer, are traveling towards or traveling away from the object that is producing the sound. Not to be confused with this one down here, which is much more common, and that is where the source of the sound, the ambulance or the police car, is traveling towards you or away from you. So you can be traveling towards or away from a stationary source of sound, or the source of sound can be traveling towards you where you are stationary or away from you. And you'll notice that when you are traveling towards the source of sound, when you are traveling towards it, we add it to the speed of sound, and this speed of sound would be needed to be adjusted to according to the temperature of the air, up 0.6 or down 0.6 meters per second for every degree change in temperature. Remember, that's that 331.5 meters per second plus or minus 0.6 meters per second per every degree Celsius. That's what V is in this equation. So you can see that as if you're traveling towards the source of the, if you were traveling towards the source of sound, so that the source of sound is stationary, but you're moving with a certain velocity, you're going to hear an increase in pitch. Your frequency is going to go up. Now, if you are traveling away, we're going to subtract it from here, which makes my numerator smaller, which is going to make the, and I should erase these here, that's going to make your perceived frequency that you hear go down. So it goes up if you're approaching the speed of sound, it goes down if you're going away from the speed of sound, but your actual frequency of that sound, of course, isn't going to change. The perceived frequency is what changes. Now, much more common is this one, where you're the one that's stationary, the listener is stationary, the observer, but the source of sound is either traveling towards you or away from you. And you can see that if the source of sound is traveling towards you, we are going to subtract it from the speed of sound, which makes the denominator smaller, which makes the perceived frequency of sound that you're going to hear greater. But if the source of sound is traveling away from you, we are going to add that to the denominator, which makes my denominator bigger, which makes my perceived frequency smaller. And again, the actual frequency isn't going to change. Now we can put everything together in this equation right here, where we have both a moving observer and a moving source of sound. Now, in this particular part of the handout, we're talking about the law of strings right here, the law of strings. Like in a guitar or violin or cello or bass or any other stringed instrument, or even in a piano, some of the things that you, I think, probably intuitively know, especially since a number of you are musicians, is that the longer the wire, the smaller, I should say, the lower is the frequency of the sound. So if you want to have a low sounding note, you would need to have a longer string, a longer wire. They are inversely proportional to each other. And so if you have one frequency at a certain length and you change its length, you're going to get a different frequency, and they are inversely proportional to each other. The longer the wire, the lower, is the pitch of that wire. The same is going to be true for diameter. If we make our wire thicker, it's going to make a lower frequency. So as my diameter of my wire gets bigger and bigger, my frequency is going to be lower and lower. And again, we can put them together like this. Now, you also know that when you increase the tension, you make a higher pitch, a higher frequency. When you tighten the wire, and you make it more and more, that you increase the amount of tension on that wire by stretching it out more and more, you get a higher and higher pitch. They are proportional to each other. In fact, they are proportional to the square root of that, of the tension. And so you can see that we can compare two particular tensions and get our two different frequencies. The last thing is the density. And the density of your wire can be increased, for example, if you wrap it in steel. If you have an acoustical guitar, you might have a nylon string, but if you wrap it in metal, you increase its density. And when you increase the density, it makes the pitch lower. They are inversely proportional to each other. And so you get this effect right there. And you can put all these things together in this equation, and you might remember you did this a long time ago in chemistry when you came up with the combined gas laws, that your pressure times your volume divided by your the number of moles and the temperature of the gas. You came up with a combined gas law that looked like this. And here we're doing the same thing with what happens when you vary one or more of these four different values that determine the frequency that's going to be produced by a guitar string or piano string or violin string. Also in this chapter, you'll get to the section on resonance in tubes. And you can have a tube that is open at both ends, and you're going to have a sound wave coming in and a sound wave going out. And I'm using here, I'm using vibrations, but technically you would have compressions and rarefactions. And then down here, you can also have a tube that is closed at one end, and this one is open at both ends. And when you put a sound coming into that tube, or when you send a sound down to the tube and there's a barrier here, sometimes we use water so that we can lift the tube in and out of water in order to vary the length that is open to the sound, and the sound is going to come down, bounce off this end, and come back. So in the tube that's open at both ends, you're going to get a resonance when the sound wave reinforces itself, and you can predict that resonance for different frequencies, and that resonance is going to happen when you have, and V, by the way, is going to be the speed of sound. So you can have you're going to have reinforcement when the sound goes through a tube that's 1/2 the length, or 2/2, or 3/2, or 4/2 of the length, and you're going to be able to get a reinforcement that's going to multiply your incoming frequency of sound by 1, by 2, by 3, by 4, by whole numbers. Now, when it comes to a closed end, when the sound bounces off a barrier, it's going to cancel itself out. And so you're going to get reinforcement when the sound goes through 1/4 of a wavelength and then bounces off and reinforces itself. And you're going to get reinforcement at 3/4 and at 5/4, but at 2/4 and at 4/4, you're going to get cancellation, where the crests and the troughs, or we should say the compressions and the rarefactions, overlap each other and cancel each other out. And so you're going to get resonance at 1 times your frequency, 3 times the frequency, 5 times the frequency, but not at the ones in between where you're going to get cancellation. Another way is to look at what your wavelength would be at different fractions of the length of your tube. 2 over 1, 2 over 2, 2 over 3, 2 over 4, you'll get reinforcement. But when you have a closed tube, you're going to get cancellation. And at the in-between ones, you're going to have reinforcement when your wavelength is 4 times the length of the tube, 4 thirds, 4 fifths, but at 4 halves and 4 fourths, you're going to get cancellation. And then the last thing that I want to talk about is something that musicians would understand. Musicians often talk about creating harmonics or overtones based upon how much they pluck a string or blow through a tube. And then musicians, including people who sing, know what an octave is. For example, if I make a pitch with a whistle, and then I do an octave higher, what I've just done is I've doubled the frequency. And if I was able to do it again and double it again, I would get my third octave. So octaves are a doubling of the previous frequency. Whereas harmonics, let's suppose I'm doing a 50 hertz sound, which would be kind of low. My first octave would be, and then I can't even get the higher one. It's a little hard to whistle that. But as far as harmonics are concerned, it's a whole number multiple of the fundamental. So if I double my 50 hertz, or triple my 50 hertz, or fourfold, quadruple my 50 hertz, and so forth, I get my fundamental is my first harmonic, and then I have my second and third and fourth when I double, triple, and quadruple it. My overtones are different. The term overtone, my first overtone is going to be my second harmonic, and my second overtone is my third harmonic, and my third overtone is my fourth harmonic. And you can see that my overtones also are, my first overtone is the same as my first harmonic, and my third overtone is the same as my, I should have said first octave, is the same as my second octave, and my seventh overtone is my third octave. And this shows you the difference between a harmonic and an overtone and an octave when you're given a fundamental, and I just arbitrarily chose 50 as my fundamental.